Hey, so today we're going to be looking at Le Chatelier's principle a little bit more. Last time we talked about how Le Chatelier's principle is all about stressing out chemical reactions. And today we're going to be looking at how do we describe the changes that occur after each stress is applied to the equilibrium. So I'm going to give you a nifty little hands-on tool that you can use to show how equilibrium shifts. Does it shift to the left? Does it shift to the right? So in other words, is it shifting towards the reactants or is it shifting more towards the products? Because remember now, we know that equations can go in both directions. So I'm going to be showing you how we can predict which way equilibrium is going to shift in order to balance out again. The first thing I want to do is go over a few things that you need to keep in mind as we are predicting how the reaction is going to change when we stress it out. The first thing I want to discuss is this idea of using brackets. If you look here, we now have our molecules like N2, H2, NH3, and in the chart, they're written in these brackets. That's because we use brackets to show concentration, okay? So we're not talking about being able to focus. Remember, concentration is how much of a substance we have. Okay? So I didn't mean to delete that text box, but when we talk about concentration, we're talking about how much or how little we have of that molecule, right? So in the chart here, okay, we're going to be looking at the concentration of N2. Okay, over here we have the concentration of H2 is increased. So that's now what these brackets are adding. We're talking about concentration. Now, if we look up here at the chemical reaction, we're going to notice a few things that are different as well. We see the double-headed arrows, right? So we have the forward reaction, which is going from reactants to products. And then now we have the reverse reaction, which is represented by this lower arrow here, which is going from products back to reactants. So again, the double-headed arrow, which represents the forward reaction, going from reactants to products, and the reverse reaction, which is products back to reactants. You're also going to notice that you see something that's not quite a molecule over here, 92 kJ. So down here, I want you to remember what kJ stands for. And if you don't remember, I'm going to tell you. kJ stands for kilojoules, okay? And kilojoules are a form of energy, right? They measure how much energy is in a reaction. And kilojoules is the same in Spanish and in English, right? Kilojoules. Now, before we even get started, we need to decide, is this reaction showing an exothermic reaction where heat or energy is exiting? Or does it show an endothermic reaction where heat or energy is entering? So I'm going to go up here and I'm going to grab a shape. I'm going to grab a circle, okay? And I'm actually going to circle, is this exothermic or is this endothermic? And to help me answer that, I'm going to look here at the kJ. I see that kilojoules is on the product side. So if we enter on the left and we exit on the right, the energy is on the exiting side. So that tells me that this reaction is exothermic, okay? Oops, and let me change that background. So I'm going to change the fill color to transparent so I can see that it is exothermic, okay? So I'm going to do that again down here. So en español, esta reacción es exotérmica. And again, if I'm pronouncing this stuff wrong, y'all need to let me know so I don't make your ears bleed, okay? So, exothermic. Now, how, again, do we know that this is exothermic? Again, we see that the energy, the 92 kilojoules, is here on the product side. So again, if heat is entering here on the reactant side and it is exiting over here on the product side. So because the energy is on the right, or on the, I guess we could say, product. Now let's say right. Okay. The energy is on the right. Okay. So, porque la energía está, I swear I can type, a la derecha. Okay. So now that we know that these brackets mean concentration, that the kilojoules, or the kJ stands for kilojoules, which is a measurement of energy, and that this reaction is exothermic because the energy is on the right, it is a product, so that means it is exiting, we can now use these clues to help us decide if the reaction is going to shift to the left or to the right, depending on how we stress this reaction out. So I'm going to create a little tool that I'm going to put down here at the bottom, okay? So I have this piece of paper here, and I have my reactants on the left and my products on the right. And again, we have the double arrow, okay? And I just took a scrap piece of paper and made this little manipulative to help me out. So how do I use this manipulative, and how is it going to show me how equilibrium is going to shift? Well, my first stress here is the concentration of N2 is increased. So I'm going to look up here and I'm going to find N2. N2 is over here on the reactant side. So I'm going to take this and I'm going to increase the reactants. Okay, you see how the reactants go up? So again, concentration is the number of reactants. So think of, a bar graph pushing the reactants numbers up. So why is that helpful? Well, that showed me that the concentration of N2 just increased. So I'm going to take my note tools and I'm going to click on the increasing arrow and I'm going to copy it. And then I'm going to paste it and drag it over here into the box. Now, not only is the concentration of N2 increasing, but I also see that H2 is a reactant as well. So I'm going to paste another increasing into the concentration for H2 as well. Now, if the concentration of reactants went up, I saw that the products are now lower. So that means that the concentration of N2 has decreased. So I'm going to copy and paste my decreasing arrow and bring it over here into my chart. Now, it's important that we visualize whether the reactants have it's important for us to visualize that the reactants have increased and the products have decreased, because this is going to tell us how equilibrium is going to shift. In order for this to go back to normal, back to equilibrium, to where the reactants or their concentration is not changing and the products, their concentration is not changing, we saw that something had to happen, okay? We saw that the reactants numbers started to decrease and the products started to increase. That's because equilibrium always shifts towards the side that is lower. So in this case, it's going to shift towards the products, and the products are located here towards the right. So I'm going to click on my note tools and I'm going to copy and paste over, okay, that equilibrium is going to shift to the right. And again, what is to the right? We see products. Okay, so we say that equilibrium is going to shift towards the products. Okay? So again, I'm having you do both of these because we, in chemistry, like to make things a little complicated. We say that equilibrium is going to shift to the right, or we can say that equilibrium is going to shift towards the products. So I'm going to reset that, and I'm going to try it again, this time with H2 being increased. So the concentration of H2 increasing. Okay, I have to look up here at my equation, and I need to find H2. And I see that H2 is here to the left of the arrows, so I know it is a reactant. So if I increase the concentration, again, I want you to imagine that I have a stack of, H2 molecules pushing the reactant side up. So I see that the reactants have increased and the products have decreased. So when I look at my chart, I find H2 and I know that it's increasing. So I'm going to go to my note tools, copy and paste, increasing. I'm going to put that in the chart. Now, H2 is not the only reactant. So when I look at N2, because they're both on the same side, they're both doing the same thing. So N2 is also going to be increasing. Okay? Now, when that happens, because NH3 is on the opposite side of the arrows, we notice that it decreased. It went down in concentration. So I'm going to copy and paste over the decreasing arrow. And again, in order for this reaction to go back to equilibrium, we're going to have to shift towards the side that is lower. And in this case, shifting to the right side because the right side is lower. So I'm going to shift to the right. Okay. And when I shift to the right, I see here I have products. So I'm hoping that you notice there's a pattern here. When we increase anything on the reactant side, it's going to follow the same pattern. So I want you to stop for a moment and predict. If I increase the concentration of NH3 is on the opposite side. Okay? It's on the opposite, lo opuesto. So what do you think that's going to mean for our pattern? Okay? So I want you to take a moment and predict. What do you think is going to happen? Well, if we're increasing the concentration of NH3 and it is a product, again, I want you to pretend and imagine that there's a whole bunch of products just stacking up on top of each other to push the side up. We see that increasing. Okay, we've increased the NH3. And we noticed the reactants this time decreased. They went down. Okay, so our concentration of N2 is going to be decreasing, and our concentration of H2 is going to be decreasing as well. So already I'm noticing my arrows here are the opposite. So I can predict that instead of shifting to the right, I should be shifting to the left. And when I look at my manipulative down here, I do see that the left side is lower. And again, equilibrium is always going to shift towards the side that is lower. So I would say it's shifting towards the left. And again, I'm just copying and pasting directly from the note tools. And what's the opposite of a product? That's right, reactants. So I'm going to say that equilibrium is shifting towards the reactants. Okay? Now, temperature. Temperature is a little different. We don't have it explicitly said where the temperature is in this chemical reaction. So we have to remember temperature is a measurement of heat, and heat is a form of energy. So going back to what we were keeping in mind, okay, kJ stands for kilojoules, and kilojoules measures heat, which is a form of energy. And we see here that kilojoules is on the product side. So we're going to treat temperature as if it were a product, okay? So if temperature is increasing, then that means as the temperature goes up, our products go up as well, because again, it is on the product side. So what does that mean? Well, we saw that anything on the reactant side decreased. So things like N2 decreased and H2 decreased. Now, because temperature is a product, we saw that all products increased, including the concentration of NH3, which is also here on the product side. So again, we're just following patterns. So when products increase, which way does equilibrium shift? It's going to shift towards the side that is lower. In this case, the side that is lower is the left side. So in chemistry, we say equilibrium is shifting left. And what is to the left of our chemical reaction? We see here that it is the reactants. So we also say that equilibrium shifts to the reactants. Now that we have our pattern here, okay, let's see if we can predict what's going to happen if we change the concentration of N2. In this case, the change is decreasing the concentration. So if N2 is increased up here at number 1, what would be the opposite if we decreased? Well, we should see that the concentration of N2 decreases, because that's the opposite of increasing. Okay, what's the opposite of increasing here? Opuesto es decreasing. And we think that the opposite of decreasing is increasing, so the concentration of NH2 we predict should increase. So I'm going to use my little tool down here to help me see if my predictions are correct. So again, if I decrease N2, N2 is a reactant, okay? That means my little bar of N2, my little stack of N2 molecules is going down. And I see that my reactants, in fact, did decrease, just like we pointed out over here in the chart. As the reactants decreased, we see here that the products went up. The products increased. So using our little manipulative over here showed that, yeah, we were right in following the opposite of number 1. So if we continue with that, what's the lowest part? Reactants. So we could say that it is shifting towards the reactants, and we know that the reactants are once again to the left of our reaction. So the concentration of H2, okay, let me reset my manipulative. Number 6, the concentration of H2 is decreased. Well, H2 is also a reactant. So if I look at number 2, okay, this is H2 increasing. If I'm decreasing, I should see the opposite. So let's see, what's the opposite of increasing? We should see decreasing, right? So anything on the reactant side should be decreasing. So both N2 and H2, their concentrations should be decreasing. Now, NH3 is a product. So instead of decreasing, like we see up here, the opposite would be increasing. And what's the opposite of shifting to the right? Well, opposite would be shifting to the left, a la izquierda. And what's the opposite of products up here? The opposite would be reactants. So we should see equilibrium shifting towards the reactants, los reactivos. So let's use our manipulative down here to see if that is in fact what happened. Okay, so if I decrease H2, that means my reactants are going down. The concentration of H2, I'm imagining all these little H2 molecules just blue, 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 leaving. So the reactant side drops. That means that the product side increases, which is what we see here and here on the reactant side, and then the NH3 increasing on the product side. And again, which side is lower? The reactant side is much lower. So equilibrium is going to shift to the left towards the reactants. Then we have number 7, where NH3 is decreased. If you would like to pause the video and see if you can try this one yourself, and then come on back once you're done, you can see the answers, okay? But if you don't want to pause the video, I'm going to keep going. So NH3 is decreasing, okay? My products are going to go down, because that's what decrease means, right? Products go down, which means what went up or increased? Both reactants increased. So I'm going to copy and paste and add this to my chart. And then the concentration of NH3, we saw that the concentration of NH3 decreased. Which side is lower? The product side, right? Which is to the right. A la derecha. And products. Productivos. Now, let's practice temperature. Again, if you would like to, if you already see the pattern and you want to try this by yourself and then check your answers, you're more than welcome to. But if you're like me and you need a little bit more practice, that's okay too. You can practice along with me. So, temperature, again, is a measurement of heat. Heat is a form of energy, and we measure that energy also in kilojoules. So when I look at my chemical reaction up here, I see that 92 kilojoules is up here on the product side, which means I'm going to treat changing temperature as if I'm changing a product. So if temperature decreases, that means my products are going to go down. So anything that is a product is going to decrease also, including NH3. I saw that as the products decreased, the reactants increased. So anything that's on the reactant side is going to increase, like N2 and H2. Now, once again, anytime we change equilibrium, it's going to want to shift. So it can rebalance itself, re-equalize. And we always shift to the side that is lower. And in this case, we are shifting to the products, which is to the right. So that's what happens when we change the concentration and the temperature. But we know that changing concentration and changing temperature is not the only way that we can affect a chemical reaction. What about adding a catalyst, adding that matchmaker, right? Bringing things together quickly. Well, guess what? Adding a catalyst does absolutely nothing to shift equilibrium. What it's doing is it's just getting you to equilibrium that much faster. So because a catalyst, whether you add it or not, does absolutely nothing to equilibrium, I'm just going to keep this last line completely blank because a catalyst does not affect equilibrium. It doesn't stress out the system. So now that you've gone through the notes here, what I would like you to do is I'd like you to go on to the next slide, and I would like you to please right here, okay, just go ahead and delete all of this. I want you to write me a summary, un resumen. So when you write your summary, make sure that you answer the focus question, which again, the focus question is up here at the top, right? Our focus question, how do we describe the changes that occur after each stress is applied to equilibrium, okay? And you are going to use these vocabulary words. So we have shift, concentration, temperature, reactants, products, left, right, and equilibrium. And I forgot to mention it on the last set of notes that we did like this, but when you write your summary, please highlight the vocab words. I know a lot of people did it automatically, but some of us forgot. So please don't forget to highlight when you use the word shift, make sure you don't forget the F. Otherwise, I want you getting in trouble for saying a bad word. You use the word shift or reactants, please highlight it. So go ahead and pause the video right now and write your summary. I would like you to go ahead and practice. I would like you to go ahead and pause the video and then come back and you will get to see all of the answers, okay? So again, I want you to practice this first. Use your manipulative. Create your manipulative there with reactants on the left and products on the right, and see if you can practice. Or maybe you've already noticed a pattern, okay? Go ahead and use that pattern here. So my suggestion is start with the keep in mind. We use brackets to show what KJ stands for, and then determine, is this reaction exothermic or endothermic? And then tell me why. So again, we're looking for those kilojoules. Are the kilojoules on the reactant side and therefore heat is entering the system, or are the kilojoules on the product side and therefore heat is exiting the system? Once you've filled in the keep in mind, then you can go back and fill in the chart. So again, go ahead and pause the video, fill in the chart, and then come back when you're all done and check your answers. So now that you're done with your chart, compare your answers to what I have here. And notice how number 9, a catalyst is added, we left blank. Why did we leave that catalyst blank? Well, yeah, it's because a catalyst makes the reaction happen faster, but it does nothing to shift equilibrium. Okay, it does not stress the reaction out. So hopefully you found this helpful. If you have any questions, you can always message me through Remind or Schoology. And if you need additional help, feel free to come to tutoring on Tuesday at 9 a.m. or make an appointment to see me. Bye.